Now, first, let me motivate why we do this work and what question we are trying to answer. Before applying the neural network in the reinforcement learning, people think that representations should have some certain properties. So people design some fixed basis representations like tail coding, so that those representations have that property. But now with neural networks, people think that neural networks can automatically learn some good representations from the data stream if the architecture used for learning is complex enough. So here comes a question. What sort of representations that the deep reinforcement learning agent is trying to learn? To be more specific, do they have the properties that people think are important for reinforcement learning? So in our work, we add auxiliary tasks to give a more complex architecture, and also we consider the case that the environment is non-stationary. By doing this, we take the smallest step we can take, which is we change the environment a little bit and do a transfer learning. So in this case, we try to understand the relationship between those property measurement and the transfer learning performance. Also, we are thinking that if for a representation, if it generalized well in the transfer task, at the same time, it has a relatively low score in the property measurement. So are these properties still important? Here's an outline of the talk. First of all, we will look at what domains we used in the experiment. And secondly, I will explain what architectures we used to learn the representations. And third, we will look at what properties we were trying to measure. And at last, I will show some result and show part of our conclusions. Now let's go to the first section, the domains we used. Here is the first domain we used. We call it simple maze. And on the left-hand side, there is the visualization of a random state. The blue pixel is the agent, and the red pixels are the wall. And the area in the white square is the goal area. But this white square is invisible to the agent. This domain takes the RGB image as the state, and there are 4 actions regarding to 4 directions. The reward function is that the agent gets +1 as the goal state, otherwise it gets 0. And then we make a small change in the environment. We move the goal state to the lower left corner. Here is the second domain. We call it picky eater. It is more like we are putting the jelly bean word in a 4-room domain, and with the episodic setting. The blue pixel is still the agent, and the white grid is still is an exit. We have 12 fixed positions in this domain, putting 12 fruits. The color of the fruits are assigned randomly at the beginning of each episode. This domain takes the RGB image as the state as well, and there are 4 actions. By defining the reward function, this environment will encourage the agent to pick up the green fruit while avoiding the red fruit. In transfer task, the change we make is to change the reward function so that the agent is encouraged to take the red fruit and avoids the green fruit. Now let's go to the second part. I will talk about the architecture we used to learn the representation. We take a similar architecture as DQN does. We put the state into a representation network and take the last hidden layer as the representation layer. We put the representation into a min network and learn the action value function, just like what DQN does. Except for the min network, we add another head after the representation layer to learn some auxiliary tasks. We have 5 different auxiliary tasks. We will give more details later. So here is the first auxiliary task we use. We call it input decoding. In this auxiliary task, the agent tries to reconstruct the input, which means the state. We don't expect the representation trained with this task can perform well in the transfer learning, but we still add it as a simple choice. The second auxiliary task is called the next agent state prediction. The agent tries to predict the representation at the next time step. By doing so, we hope the agent can the representation can capture the transition dynamics. The next auxiliary task takes one step forward. The agent predicts the discounted summation of the representation. The fourth auxiliary task is expert target. In this task, the agent tries to predict information that might be useful for learning. For example, like the position of the agent in a maze, or the color of some important pixel in the picture. But this auxiliary task would require people to define the useful information, and it is not always capable to do that. So we only add this task as a sanity check. The last one is auxiliary control. In this case, we add a different goal state in the auxiliary task, or we use a different reward function. The task in the auxiliary task will not affect what the agent should learn in the main task. And the agent is trained in the auxiliary task to learn a different set of value function. By doing this, we hope the representation can encode different value functions with a shared transition dynamics. And here's the conclusion of all 5 auxiliary tasks we are using. First 4 of them are based on predictions, and the last one is based on the control. Now let's go to the third section. What properties did we measure? And please notice that this is just a subset of all properties that the community thinks a representation should have. And this is just a starting point of understanding the representation learned with neural network. The first property we measure based on the assumption that features of the representation space should be orthogonal. By features, we mean each bit of the representation. The next assumption is that the correlation between pairs of features should be small. We call this property a decorrelation. The next one has the assumption that the representation encodes most nonlinearity of the dynamics, so that when we deal with some task, learning a relatively simple value function would be enough. We call this complexity reduction. And next, it is dynamics awareness. The assumption is that nearby states should have similar representations, and far apart ones should be dissimilar. By nearby, we mean that it is easy for an agent to get to one state from another. And by far apart, we mean this process would take longer, or it's harder for the agent to do so. The next property is linear Poissian accuracy. It's based on the assumption that people think the representation should have a large enough capacity to include all the useful information it needs to deal with the current task. So we train a linear transformation to extract those information from the representation. The next one is diversity. It assumes that the representation should be able to handle multiple value functions rather than being too specialized on one value function, because we want it to be able to generalize. The last one is non-interference. The assumption is that when updating the value function of one state, other states are not negatively affected. And here's the conclusion of all 7 properties we are trying to measure. And then we show some results we have. First, I'll explain the pipeline of our experiment. In the first step, we do a representation learning using the architecture that we explained before. In the second step, we take the learned representation and do a transfer learning. In the third step, we measure the property of the learned representation. First, we show some learning curves. These are the learning curves of the representation learning step in simple maze. And please notice that our goal is not to improve the learning performance using any of the technique. We're just trying to understand the relationship between the property and the transfer learning performance. And those learning curves are here because we can, I just want to show that we take the representation after the agent has a reasonable performance. That means it learns a reasonable policy.
Yeah, I'm just going to ask a question that I would imagine maybe someone has is, or maybe just make a comment, that each auxiliary task is only one of them is used. We're not using all of them at once. So even though that picture suggests all of them are being used at once, only one is used.
Oh, sorry. Yes, only one auxiliary task is used at one time for one representation.
So and that's why there's multiple lines. Okay.
Yeah, thanks for make it more clear. And here are the learning curve for the transfer learning. Again, we are not trying to do the comparison here. We just to show that in transfer learning, our representation can, our agents can learn something with the fixed representation network. And here are the learning curves of the PK-ITER in representation learning step. And here is the learning curve for fixed representation in transfer learning. And we can see that for all the representations, they have a relatively bad performance here, although it looks like they are converging. And all of them are not better than our baseline, which is learn the DQN learning from scratch. So we added another setting in PK-ITER, which is the transfer learning with fine-tuning. By fine-tuning, we mean that the representation network is not fixed anymore. It can be adjusted according to the loss it gets in transfer task. And we can see that the performance of those agents are much better than before.
I'm going to interrupt you one more time, Han, because again, another question I imagine someone might have. Could you go back to, like, let's say the first plot and just sort of explain what's going on in that plot and what's an interesting thing to take away from it, if anything interesting that can be taken from it? Or pick one of the plots and maybe dive in depth onto what's interesting about it?
You mean the learning curve of the representation learning?
Yeah. I guess maybe the question is, what's the goal of showing me this learning curve? What am I supposed to get from it?
Oh, the purpose of showing the curve here is just to show that we are taking the representation after the policy is converged. Like we are not randomly cut the absolute and take the representation to do some measure. And we will do the compare between the property and the transfer performance later with a different data format.
Okay. So you just wanted to convince me that you didn't just run these agents poorly. Okay, I get the goal now.
And now we will change the format to show all of those data. And first I will explain the X and Y axis here. On the X axis, we show the performance of each representation we have. And on the Y axis is the score. We normalize all numbers to be between 0 and 1. For scores for property, it's just the measurement. And for scores of the transfer learning performance, we show it based on the area under the learning curve. And it's also normalized. Now we go back to the transfer learning performance in simple maze. The transfer performance is shown with the pink bars, and we can see that expert target prediction, auxiliary control, and successor feature prediction auxiliary tasks all improve the transfer learning performance. And input decoder would hurt it. And in PK-ITER, we add another bar showing the transfer performance with fine-tuning. And in this case, auxiliary control, next agent state prediction, and successor feature prediction will improve the performance, and input decoder still hurts it.
Hey, Han, there's a question in the chat.
The question is, so if every training is on one task, and we have only one position for the goal, and yes, it is for all the main tasks, we only have one goal, except that when we add the auxiliary control as an auxiliary task, we can add more than one goal in the auxiliary control task. At the same time, the main task still has only one goal. And if we go back to the transfer learning performance here, we notice that the input decoder consistently hurts the transfer learning performance. Now we go to the measure of the property and the relationship between the property and the transfer learning performance. One thing I want to show is the measure of the orthogonality, which is shown in blue bars in this plot. We notice that for representations with high orthogonality, they generally have a relatively good transfer performance. For example, in simple maze, we can look at the expert target prediction, auxiliary control, and in PKiter, we can look at DQN and expert target and auxiliary control. However, when we look at the representation with a relatively good transfer performance, for example, the successor feature prediction in simple maze, it is not necessary that the representation has a high orthogonality score. And sometimes our measure just show an unclear pattern. For example, when we measure the diversity, it is hard for us to make any conclusion according to this result. And also there are cases that we see a similar score for all the representations we have. For example, when we measure the non-interference. Now here are some conclusions. Because of the time, I'm not able to show all the plots that we have, but I would show what we've seen in our experiment in the conclusion section. First one is what we've seen. A representation with a higher orthogonality tends to perform well in transfer learning. However, a good transfer performance does not imply a high orthogonality score. And second one, all representations have similar score regarding to non-interference. And some measures do not show a clear relationship to the transfer performance. And sometimes they show an inconsistent pattern in both domains. For example, the decorrelation measure and dynamics awareness measure. And linear probing accuracy and complexity reduction would have a high property score even when the transfer performance is bad. So all of these results make us consider that we may need to reconsider the equation we used to measure those properties. And last, we also confirmed that the auxiliary tasks help with transfer learning, but we need to choose them properly. And that's all. Thank you for listening. Is there any questions or ideas?
So just a quick clarification. So in some of the later plots where you showed the transfer learning performance in like pink or something and then some other property, was it for the fine-tuned representation or just the fixed one?
So which part do you mean?
So like one of the later graphs, like I think 48 or something.
40.
Maybe. Or yeah, 50. Yeah, maybe this one, 49.
This one?
Yeah.
Oh,
So
this one.
Yeah. So are these the pink transfer performance ones? Are they with a fine-tuned representation or the fixed one?
It's the fixed one. Because when we measure the orthogonality, we just take the learned representation and do the measurement. It's not actually about the transfer learning step.
I see. Good. Yeah, and could you just keep the graphs like on screen so that we can just stare at them for a bit?
You mean this slide?
Yeah, this one is it.
Hey, Han.
Hi.
Thank you for the talk.
Thank you for listening.
You talked about orthogonality and you talked about correlation. And can you explain what the difference is between these two?
For orthogonality,
Yeah, and
I think we are emphasize that for each feature that we learn, they should be different. Like they should be orthogonal to each other. So we can say they are learning like the different dimension in the dynamics. And for the correlation, we want to emphasize that for any pair of the feature, like they should have a small correlation. So I think those two properties are same when we centralize the data, but it's not always the case in the application. So we still measure those two properties separately.
Just to add to what Han said there, yeah, I believe that if you take your feature vectors and then you were to like center them, you go compute their mean and subtract the means off of all of them, then correlation and orthogonality would be equivalent. But orthogonality doesn't require you to do that. So they are technically different measures if you don't do that.
Thanks. I've got one other little question. So all these methods have gazillions of hyperparameters, and yet you didn't really talk about, you just compared as if there was one method with no, so how could you, how did you resolve the fact that they all have many hyperparameters, and how could it be done fairly?
So we fixed most of the parameters, and we mainly focus on sweeping the learning rate. So for both the representation learning step and the transfer learning step, we sweep the learning rate in a fixed list, and we do 5 runs, and we pick the learning rates with the best performance and do another 30 runs.
What other hyperparameters are fixed? Like the network architecture would be a fixed hyperparameter. What other things did you guys fix?
Oh, sorry. The network architecture are not fixed. We sweep them until we see the setting that makes the agent to learn a converged policy. And all representations have a fixed length of time step, except for the input decoder in simple maze. It has a relatively longer learning because we want to see the performance is already converged. And at that time, we cast it and take the representation.
Okay, so I guess maybe what you're saying is one of the ways the hyperparameters are selected is simply to try to pick them so that all the agents are learning quite well on the first task. Well, maybe, Rich, one justification for why it may be more okay to fix some of the choices, like picking a larger number of steps so that all the agents sort of get to see a good amount of data. And I don't know, I thought somehow the network architecture was the same for all the methods, but I guess that's not the same. But in any case, other choices being fixed is that it's not really saying one method is better than the other. It's sort of saying in a standard setting where the agents are actually able to learn something pretty good, what kinds of properties could emerge. So it's more like a demonstration or demonstration of both what kinds of representations could emerge and also demonstration of how you might measure some of the properties that emerge. But I'd love to hear you say it's completely wrong for X reason, or you should have done Y.
I just don't have confidence that the results would be the same if the hyperparameters were different.
So, for example, if the step size was no, actually, let me pick a different hyperparameter. What kinds of things might you might imagine? Like, let's say we didn't run it for so long, and so if we didn't run it so long, it maybe wouldn't have tailored itself so much to task one, and we would have seen very different transfer performance or something like that. Look, Zahir's unmuted, so maybe he can say something. As someone who actually ran the experiments.
So I was about to say that, so we did sweep over architectures, but we found one architecture that worked for all methods. So you are right. So Rich is right that we cannot say confidently that these results would generalize to other hyperparameter settings, but we were using some of the obvious choices of hyperparameters without tinkering them a lot, just to see what we will end up seeing, right? So you look at performance and you figure out some hyperparameter settings, which are natural choices, which get you to certain performance. And then once you achieve good performance, you compare across methods how these properties differ.
Yeah, right. For one environment, we are using the same architecture for the representation network. And we cannot control the rest of them because like we're learning different auxiliary tasks and they may require different capacity.
Right. So my question is, so let's say you want to do what we want to do. How will you take care of this issue? So this is to the rest of the people who are listening to the talk.
It feels to me like to really establish something clearly, you'd have to just maybe focus more on the one thing you would like to establish. Here we have sort of a broad brush, it's sort of a first investigation. What if you kind of do kind of normal things, what ends up winning? But you don't really know if any individual result is going to hold up to a more rigorous test. I think you have to focus on something and think about it.
Well, we weren't exactly trying to get one thing to win. Like we weren't trying to show auxiliary control as a better auxiliary task, say the next agent state.
I'm not asking about winning.
Okay, I heard you say winning.
One clear conclusion that you can draw that has some generality.
Right.
So like this question that I would be sympathetic to is that auxiliary tasks improve the generalization, improve the representation. And I a lot of people have talked about that, but I don't think we've really had a significant believable evidence for it. I mean, it's like everything is preliminary results. And then, we confirming preliminary results, not really satisfactory because, that's what you wanted to happen and you got it to happen. It's not like, what if someone believed it wasn't true? Have you really shown it to someone who didn't believe it?
So
I want to say one null hypothesis is that we get good generalization in representation in neural networks because people work at it. They like things until they find something that gets good generalization. And if that's kind of a difficult null hypothesis to disprove because it's sort of a general problem with this area. But I want to say this. I think what Han, that was a good talk today, and I liked it. I like the results you have. I'm just trying to make it better. Good.
Thanks.
So
sorry, here. I was going to say something too.
Go ahead.
Well, one thing that was sort of the goals behind this was before even asking a very specific question. That the title is something about emergent representations. So we kind of wanted to know what's even happening. Like when I train DQN agents, what kinds of things are emerging? And so in some sense, we're reporting our exploratory analysis. Now, it could be more worthwhile to say instead, somehow actually to do that exploratory analysis, and then maybe dive deep now into some of the things that we've noticed. Yeah, it could be something like that.
Right. Okay, so what I want to add to what Rich was saying is that, so if you make a claim that auxiliary task help with generalization, that is obviously false because it depends on the auxiliary task. You can come up with an auxiliary task that can screw you up, right? So let's say if you want to make a general claim, you have to make some choices, and then you can make a qualified claim that, oh, my successor represents my auxiliary task with successor representation with this parameter setting is showing me this, which suggests that maybe this general claim is true, but you cannot definitively conclude that because, as you said, there are so many hyperparameters here. So I'm just thinking, is there a way to even make a definitive claim and given the choices we have? I think you can only you can come up with experiments that can suggest you something, and then you can sort of, like, how would you go about making a definitive claim here, given the number of choices we have?
I think the first thing would be to think about what the claim might be. I mean, right. You said yourself that, Zahir, you said that the idea that auxiliary tasks, always help or something is just obviously not going to be true. It's not really a good candidate for being true. You need to express it more precisely. And I think there is need at that level to think of what would be a plausible question, hypothesis.
Well, actually, I was hoping that some of the hypotheses would be about the properties, like complexity reduction is, highly correlated with transfer performance or something.
But we design the tasks, and we like them to be simple, and we designed problems where the transfer, if you're simple, you're going to transfer well.
Right, regardless of properties.
Potentially suspect biases of the experimenter. Yeah.
It's true that when we started putting together these results and trying to find correlations, we literally had like 5 numbers to find correlations from, and our immediate instinct was, I wish we had 1,000 numbers where we had like many domains and many agents, and we could actually see correlations amongst many agents. So here's a deep mind now.
It's different. It's really just the same. DeepMind has one with 120 tasks, but it's just as suspect because some person designed those 120 tasks, and if they tend to have some way of doing it, they make 120 instances of it.
Right. We need to have like a domain creation workshop or something. I don't know. I'm not really sure we can do.
I think we need to think harder. About what the question is.
And maybe we could design some environments that would be trying to break our agents or probe different, break certain auxiliary tasks or something. I'm not sure. You're right. We need to think harder. I'm also going to state out loud that I actually don't like the idea of auxiliary tasks. I actually kind of think it's a bad idea. So the choice of using auxiliary tasks is to say, let's understand existing representations. And this is a strategy people use. Not necessarily because I actually want to show the auxiliary task effect is true. Or maybe one of the reasons we didn't end up posing that question, because I don't even like it. And just to be more clear, it's not that I don't think predicting many things is a bad idea. I think that's a great idea, but why are they auxiliary? Like, I feel like our agent has so many things to predict about the world anyway. They are primary.
Martha, I just want to say I really agree with that point of view. I haven't chipped in yet, but I've been thinking a lot about how we define the representation. And I tried to slice it one way or another. Is it like the last layer before we do something we think is useful with it? Is it the thing we put at the beginning and then we put a bunch of networks afterwards? And the end result, it really struck me that, in fact, the entire learning machine itself in some way represents the concepts we care about. It's like usually it's a representation and maybe a value head or a policy head, but in the end, the whole thing is in fact in some way or another representing the concepts we care about. In which case, then your point is really bang on: is that the auxiliary tasks or whatever tasks we have for it are in fact all being captured in that representation. They're just part of the world that the agent lives in, and it doesn't seem sort of reasonable to think of them as special. It seems that we should just think that, no, the structure of our learning machine is going to be fit to whatever kinds of environments we place it within. And therefore, our auxiliary tasks, we pick good ones or bad ones, it doesn't matter, because those are, in fact, the world our thing lives in. When we try to transfer it to another world, that just seems kind of weird. But then again, maybe I really still don't understand transfer learning.
I'd like to pipe in with a small comment. This is Joseph.
Joseph.
Yeah. So I like this approach. I think trying to find a good representation is an important problem. It's really rather difficult to wrap your head around. And well, this is an off-the-cuff comment, maybe a bit of a joke, but if finding a good representation is difficult, maybe we should try and figure out what are the properties of a bad representation. Like do we have any idea of what the scale of goodness of a representation is? Can we tell a bad representation, right? And perhaps there are some notions of bad representation, like it can't represent anything, like the zero vector is a bad representation. But then as we try and expand the notion of what a bad representation is, maybe we could start to move towards what our notions of a good representation are in contrast.
I feel like the notion of a good or a bad representation is completely subject to your goals with that representation. As an example that is just, it's a pathological example, but if you, for instance, wanted to take an environment and learn a function that generates a cryptographically secure random number sequence from that environment, that's going to, like, your goal is to generate something so deeply decorrelated from something that was correlated in the beginning. So rather than learning structure, you're learning like anti-structure. And we don't want totally decorrelated representations for meaningful learning, but maybe if our goal was learning random number generators from environments, we would. I don't know if that makes sense, but.
Yep,
Kirby, you're starting to think, so that's really good.
I think this also comes up in the preference between having like compact lower dimensional representations and like expansions, where maybe you're like in a memory limited setting, and so a compact representation could be good. And maybe you're not learning incrementally. So again, a compact representation might be a finding. Compact is maybe the wrong word, but like lower dimensional representation. So some representations you're going to use to learn incrementally, and some representations you're just going to take a big batch of offline data and try to compute the best function you can from them. Those are just two very different settings.
So are these, so are you thinking that these two different settings are applicable to two different problems, or that you use a combination of them to solve the RL problem?
You mean use a combination of lower dimensional representations and expansions?
So you're saying these are two different settings, like you're learning online and then you have this batch setting. So are you doing a little bit of both of these as part of your solution to solve this overarching RL problem? Or you're just thinking these are like two different problems and like they live in silos? And
yeah, my bad. I'm not really being very precise right now. I'm sorry. I guess maybe the settings I was imagining that are different are you're interacting with a stream of correlated data, and even if you get to store some batches of data, that data is always going to have some correlation, because you're going to preferentially look at more recent data, which is different than, let's say, an IND setting. Both could use batch strategies, but the data correlations, I think, are an important distinction.
So I'd like to say something useful to this discussion here, but it's hard to say anything useful. One thing that I like is maybe the sentence, or that's useful way to begin is I like to say first thing is to recognize that there is no magic. to representation learning. And in some sense, the belief that neural networks somehow give us good representations is a belief in I want to say, a kind of magic of neural networks. And I don't believe there is any magic. If there's no trick that's going to give you somehow good representations. Instead, what we should be looking for is somehow that the data will in other words, if you're going to have a representation that's good for whatever problem you're working on, the data has to tell you that in some way. There's no way you're going to generalize well without having a reason to generalize well. In order to generalize well, you have to have seen different ways to generalize and seen empirically that one way works better than the others, and that's the one you've chosen to use. That's what it would mean for there not to be magic. Okay? There has to be a reason to generalize. It has to be visible in the data.
So so is you in this particular instance, is this the experimenter or algorithm designer, or are you talking about the agent? Whereas agent sees different ways to generalize.
Yeah, the agent.
All right.
Yeah, I agree with that. Sometimes we say, why don't our agents ignore colors of pixels, and why don't you run them on an Atari game with the pixels colors change? Why don't they do well? Well, they were never trained in that setting, so it's why we're even expecting them to do well. I suppose our experiments are in that setting because we never trained them with the red and the green fruit being swapped, is maybe something you're implying.
There's a lot of work where we say, oh, I think you should generalize like this, and so my agent should do it. But how would the agent know that that's the right way to generalize? The only way is if they've seen data, and then you end up presenting them a lot of data, and then you may be disappointed because they're learning too slow. We have to adjust our expectations. We shouldn't hope for magic. There's no magic.
I totally agree with that. But that's not the only way our agent does generalize. Like that would be like pretending we didn't accidentally encode in any kind of structure into our agents. We always do encode some structure. So they will generalize not just from data, but also from things we've encoded into the agent. But we shouldn't expect it to generalize in ways that we didn't tell it to generalize or we didn't encode in some way. I agree. That's just like, it doesn't make sense that people would expect that.
But that's what happens. Like we make them generalize in a certain way, and then we're happy that they do. Okay. And the only alternative is that we don't make them generalize any particular way, and we give them enough time to figure out what is the best way to generalize in that particular setting they have. And how would that make any sense? Because there's no free lunch theorems and stuff like that. And the only way it makes sense, and this is, I think, actually, I think this is an insight, is that this idea that the world is much more complicated than the agent, and so the agent, it's okay for the agent to see things multiple times because he's not going to be able to remember them all. And so if your agent is limited, then I think you could make a setting where you could rigorously, perhaps, talk about representation learning.
So just a quick comment. So representation learning is a very hard problem. And a while ago, I used to think that, the AI problem is, the representation learning, RL, and I can choose to focus on just the RL part of it, given good representations. And then I'll let somebody figure out what the representational part of it is. But yeah, I've recently come to realize that it's more like this. And it's not just a bottom-up thing that given a representation, you learn to do well from it. It's top-down as well. So what you can do affects what you can see. Like basically, your agency determines your sensory inputs as well. And so yeah, I think we all have to get our hands dirty in both of these places in order to figure something out. There's no easy escape.
As I said, okay, good. Thanks, everybody. I see it's 5 o'clock, so we should probably let people go. Thanks, everybody. Thanks, Han, for a very stimulating talk and interesting results.
Thanks, Alan.
Thank you for listening.